Sure. Good morning, Commissioners. My name is Rachel Rowe. I'm the Ferry Operations Division Manager with Skagit County Public Works. And just to give you a little bit of history about why we are here today, we're here with Art Anderson Associates. They're a naval architecture firm and located in Bremerton, Washington. Skagit County has worked with Art Anderson Associates several times in the past. They did a mid-body extension study for us, and a number of years ago they assisted us in capital planning efforts. Most recently, we started working with Art Anderson Associates for an as-needed contract for naval architecture and marine engineering services. That was in the fall of last year. So about that time, actually it was in December of last year, when Joe Payne with EESI Marine came and presented Skagit County with a concept for an all-electric ferry. And we were advised by Art Anderson Associates at the conclusion of that presentation that our next step would be to conduct a propulsion study to determine the feasibility of such technology for the Guaymas Island route specifically. We started working with Art Anderson in the early part of this year, and today Eric Engelbrecht is here to present the final propulsion and power study. So I'll turn it over to Eric.
All right. Thank you, Rachel. Thank you, Commissioners.
Good morning.
It's a pleasure to be here to present. So let's get started. The agenda, it's going to follow the general structure of the propulsion study, and I'll walk you through the various elements of it, background, the methodology that we utilized, power required that was determined, the operating scenario and battery options that we reviewed, annual energy requirements, naval architecture considerations for potential concept design, regulatory body concerns, alternative propulsion analysis, and then some conclusions and recommendations for you going forward and for Public Works. The purpose of the study was fourfold. It was determine the maximum thrust, power, and energy requirements for an all-electric ferry concept on a current ferry route. Determine the propulsion configuration for a new all-electric ferry concept and the resulting battery power requirements. Evaluate some preliminary U.S. Coast Guard tonnage ratings and how that would impact a potential design. And do some comparison of different types of propulsion versus all-electric for this particular route. The main methodology that we utilized was that we subcontracted Cummins Northwest to do data logging, where they connected a C-185 data logger to both engines. They recorded engine parameters as well as GPS data for vessel position, distance, and speed. This was done over 11 days of operation, started on the 29th of March at 6:30 p.m. and ended on April 9th at 4:30 p.m. So a total of 11 days, as I stated. The engine parameters that were recorded were engine speed, percent throttle, percent load versus torque, fuel rail pressure, engine power output, which was calculated based on an algorithm that's loaded into the ECM. We tried a couple of other methods prior to that. The primary best method that we focused on, which wasn't viable, was to go and actually set up to take torque readings off of the output shaft of the engines. However, the make of the shaft wouldn't allow for that. So next we took an initial look at possibly putting fuel monitors onto the engines, but in initial discussions with Rachel, that just wasn't a viable option to invest in that type of equipment for something of such a short duration and specific need. So then we went and we did an average of fuel usage to get some initial numbers as we proceeded forward with bringing Cummins on board to hook up their data logger. So you can see here, this was the data that was recorded. The ferry route, it's approximately half of a nautical mile one way, so just over 1 nautical mile in total in the round trip. We point out there the Anacortes terminal and the Guaymas Island terminal. And so you get a sense there of the operation. A better image is the next one, and this is all the sailings for 11 days. And I wanted to put this in here to illustrate some of the elements that we highlight in the report, which is that your ferry operates in a pretty unique area. A narrow channel, high currents, high winds, lots of vessel traffic. And you can see here in just an 11-day period, the day-to-day demands required a lot of the operators. I can't begin to guesstimate as to what caused some of those routes to go the way they did. Rachel could probably provide more insight, but it could be a number of issues. So given that, one of the key outcomes that we wanted to achieve was getting a firm determination of thrust requirements for the new vessel and really understanding what is really driving the power demand. So to give you some technical insight here, we utilized the GHS geometry file from when we did the mid-body extension back in 2006. In agreement with Rachel, we targeted that a 25-foot extension for a potential new vessel or a 150-foot long vessel would be an adequate initial concept size for us to do an evaluation on. So it worked out well in that regard. So with that, we calculated underwater lateral plane at the max draft, determined that a 25% thrust increase would be required to clear the dock at Guimas Island at a 45-degree angle, which is where the most power demand is called upon for the vessel when she departs there. This would lead to determining that twin 500 horsepower thrusters will provide the 240 kilonewtons of thrust that's required so that you can depart that terminal in a high knot current situation, which worst case scenario is we estimated about 3.7, 3.8 knots. So then if you're assuming that we have 30 kilowatts reserved for ship electrical loads and 500 kilowatts is what we're going to be targeting for the power available from each battery bus, a 470 kilowatt or 630 horsepower thruster could be powered from each bus. Again, exact size of the thruster can be determined during final design because this is only at the concept level that we're having this discussion. But it's reasonable to assume that the potential new design would have anywhere between 500, 630 horsepower for each thruster. And that's a key element in doing the on-site ride-along discussions with Rachel and her team is when you're operating that ferry, as you could see here, you need a lot of power on demand to maneuver through that channel and all the various conditions that you may encounter. Plus any emergency runs is what we defined them as, where it would be fire or medical, which would necessitate that you're taking a heavy load, fire trucks and other support services across repeatedly at high speed, regardless of condition or time of night. So with that, it was pretty obvious at that point, but we wanted to state it unequivocally that a propulsion system utilizing traditional propellers and rudders and tunnel thrusters, while considered, it doesn't appear to be adequate at all for the lateral thrust requirements that would be needed to move this vessel in a high knot current situation off of the Guimas Island terminal and give the maneuverability and the power capability that would be needed by the operators on that ferry. And so we're going to be focusing, I think, going forward, looking at new designs strictly on azimuthine thrusters, and we recommend them for any potential replacement vessel that may be built. So the power required, so what did we see? So this is an image, and this is in the report, of the highest power demand that occurred during the 11 days. And this was on Sunday, April 3rd. This was an emergency run. So it was, I believe it was a medical, if Rachel checked the log. Point being is that there's a number of different conditions that occurred that required the ferry to be reliable and safe and respond quickly to emergent needs of the citizens of Guimas. And so the highest power on a round trip, the peak off of both engines, is that we saw 952 kilowatts. And that was one of the main targets of this study and getting the data, because this drives everything else going forward in terms of how we would size the battery going forward. with that, we correlated over the 11 days based off of current, which you can see here down on the bottom in the blue, versus the actual energy in kilowatt hours that was used on the round trips. And you can see a general trend here where you had higher knot currents. The energy demand was significant. And we saw a peak, again, it was that April 3rd date, of 110.5 kilowatt hours on a round trip. And so keep that in context with previous discussions that have been had about this concept and the feasibility. On the average, if you're taking a look at straight average based off of fuel consumption, for example, you're looking at somewhere between, the numbers have varied between 70 and 80 kilowatt hours per round trip. But the current and the conditions in which this vessel operate dictate on a round trip, you're going to peak out at 110.5. And this is a snapshot over one 11-day period throughout the year, but it's pretty indicative. So with that going forward, we said, okay, how are we going to size this battery? And so we recognize that when you have a larger vessel, potentially 25 feet longer, with a higher thrust demand, have a 25% additional thrust requirement, and you've got a kilowatt demand at 952 kilowatts max, we said, well, what's the appropriate level of buffer that we need? The schedule can demand or dictate that anywhere between 23 to 28 scheduled runs need to be done during a given day. Sometimes as many as 26 on the weekends. And then you have 4 additional trips that are available to the operators for unique conditions or days when there is a really high demand and they have to do 4 additional runs. So in order to appropriately buffer for that, we said, okay, at 500 kilowatts and above, we're going to put a 25% buffer onto it. So anytime that vessel is inbound or coming in, is departing the respective terminals, whether it's Anacortes or Guaymas, we're going to say put 25% additional kilowatt demand on there. And then for any of the transit period, we put additional 5% on. And that's for incidentals during the transit for the additional thrust requirement. And then we did that for each data point, and then we re-averaged. And so from there, we went and we said, we dictated or began to develop an operational scenario. And that scenario, working with Rachel in our discussions as we reviewed the report, would be determined on the unique tide conditions. This is a snapshot from the April time period of predicted current. And you can see here the extreme swings in the current that are occurring at Guaymas Channel. And in particular, you can see down in the middle, in the morning period, the current can get as high as 3.7, 3.8 knots. And so for an operational scenario, what we agreed on is that we divide the 4 tidal shifts into 3 periods because one of them is occurring during the middle of the night or during the evening period when the vessel's not operating. And we said, all right, let's identify one of these periods, period 1 in the morning, as the one that would have the highest power demand or energy requirement of an all-electric battery ferry. And in the rest of them, we said, well, we could just focus those more in terms of the average kilowatt hour usage. And so you can see here in this chart, that's what we're demonstrating. Time period 1, feasibly a time period during the day when you have the high knot current situation. We added on that buffer above the 110, and it averaged out at 118.2 kilowatt hours. And in the remaining time periods 2 and 3, we said, let's go with the average that we found from the overall data of 77.4 kilowatts. We added them up with their respective periods, and then came up with a total of predicted per day megawatt hour usage. And so for that, from the previous chart, you saw a total for one full day, all 3 periods, that's 2.339 megawatt hours. And that's energy usage. And for the context of our discussion, megawatts is Megawatt hours, kilowatt hours are a measure of energy consumption, while kilowatts by themselves are an indication of power demand. So for battery sizing, we want to focus on kilowatt hours, but kilowatts are also indicative of the horsepower requirement, so it helps to translate between horsepower to kilowatts and in energy usage. So in general, when you see kilowatt hours, think of fuel consumption or gallons of fuel being used as a comparison. And then when you see straight kilowatts, think of it as a comparison to horsepower. So we added that buffer, and we said, so we did the total for the 3 periods. We had the buffer for 4 round trips to account for extra runs on high traffic days, which is indicated in the schedule. And we came out with an additional 309.6 kilowatt hours. We added an auxiliary electrical load requirement. So there's currently an auxiliary genset on board the vessel. It's rated at 40 kilowatts. It has 30 kilowatt hours of consumption. We assumed an 18-hour day, and we averaged that out at 540 kilowatt hours. So a total average of energy consumption for a potential vessel is 3.189 megawatt hours on a given day. That then led into, then from there, the report shifts into what we looked at in terms of operating scenario and battery options. So with respect to that, you have to ask yourself what the technologies, what do you want to accomplish? Previously, we looked at 2 technologies. We looked at vanadium flow batteries using a vanadium redox solution, which you're familiar with, being supplied from UET Technologies. And also we looked at lithium-ion configurations. If you're targeting to go with 1 charge on a single day over the evening period when the vessel's not operating, the only chemistry technology currently available would be the vanadium flow battery. Now, if you're looking at setting up an opportunity charging or an intermittent charging scenario that works with the schedule, that would lend you towards lithium-ion. Ultimately, how you set up your lithium-ion configuration is contingent upon what you've determined as the ideal scenario for operating the vessel, given the schedule and the potential demands for various seasons of the year. But from a high level, general trade-off or review and comparison of the 2 technologies is in this table, which is in the report. From a cost standpoint, your vanadium flow battery will be lower than your lithium-ion battery. Its weight will be significantly higher versus lithium-ion. The VRB flow battery's volume will be significantly higher because of the way that it's constructed and the chemistry that it uses. Maintenance, in comparison to lithium-ion, is substantially lower. Safety, both are good. Vanadium redox is excellent. Complexity level is much lower on VRB versus lithium-ion. Reliability, we felt that VRB had more reliability versus lithium-ion. The efficiency, lithium-ion has more efficiency. It's an excellent, up there in the mid to high 90% efficiency level, while VRB is lower. Estimates are around 80, sometimes as low as 75%. Cell degradation is a major consideration with lithium-ion. You will have to have a cell replacement strategy, which adds in more complexity with the long-term maintenance and viability of the technology. But as previous presentations have demonstrated, the chemistry and the technology is always evolving. So that could change over time. With VRB, there is no cell degradation. The solution's good for 20 years. In the charging cycle, again, you'd have to have an opportunity charging schedule that'd be required for lithium-ion. VRB, you could go once daily if you chose to do so. In terms of annual energy requirements, I won't go through item by item on this table, but it summarizes, and this is in the report, you would see a total estimated annual utility cost to the county that would be slightly lower for lithium-ion. And that's mostly driven by the system efficiency. Lithium ion is more efficient, as I stated, than VRB flow. So naval architecture considerations. So for us, we set up the general vessel parameters and performance considerations for the new concept as follows. We agreed it would be all electric. We agreed that a new concept would certainly be 46 CFR subchapter T, small passenger vessel, essentially under 100 gross tons. Similar shape to the existing vessel to accommodate docking at the existing terminals. Length 150 feet, breadth 52 feet, maintain a draft of 6 feet. 2 each azimuthine thrusters was determined, as I previously discussed. We would look to enhance the vehicle capacity to upwards of 30 cars, increase the passenger capacity to 150, and crew would that'd be to be determined depending upon the needs of the technology that would be put into the new vessel design. We'd look to achieve a speed around 10 knots, targeting runs of 23 to 26 per day, very similar to the existing schedule. So with respect to tonnage, the thing to consider here is that tonnage is a measure of the volume of the actual, of the hull. So it's not necessarily a representation of weight per se, but it's recognizing that for a certain size of hull and displacement, you want to have a certain level of capacity. And you have to be very deliberate in your design as you go through that to ensure that the representative volume allows for you to remain under that subchapter T requirement of 100 gross tons. And so with respect to that, what we're trying to indicate in our write-up in the report and with this table is that if you're starting with a clean slate, a fresh design, you have a number of different options. There's a number of different design techniques that you can utilize so that you can ensure that you're under 100 gross tons and that you have a lot of variability in your length, your beam, your depths. And that's what we're trying to represent in this table. All of these ferry vessels are in the subchapter T requirement, and they vary in length and beam and capacity quite significantly over quite a range. So I don't want, the main point in working with Rachel was that we wanted to communicate to everyone is that you're going to have plenty of options when it comes to setting up this design in terms of capacity. We chose 150 feet because we needed something that we can run the analysis on, but going forward, you can remain under subchapter T, your manning requirements and your Coast Guard requirements quite easily with a number of variabilities in the design development. Weight. Now here, this is very specific. We were wanting to ensure that in a comparable conceptual all-electric ferry that you're going to have enough capability with these VRB flow batteries of such a large size and still maintain or get the capable performance that you need for the vessel. So typical, and we go into some more detail in the report, one of the coefficients or comparable metrics that we like to use in naval architecture is design length ratio, the displacement to length ratio. And in that, we're taking a look at the actual displacement that's caused by the hull due to its weight and running it through a calculation and then making it comparable. And what we saw is that the conceptual all-electric ferry, based off of the mid-body extension, going up to 150 feet, is very similar in that ratio comparison. So you're looking at something that's going to get very similar performance, even with the additional weight of these flow batteries potentially. Lithium ion, it's not even worth commenting on in that regard because it is so light. It has very little effect. So such close agreement shows that the all-electric ferry concept is feasible from a naval architecture design consideration for this vessel on this route. Rachel and I did go and visit with the local officer in charge of marine inspection, who provided us a very good summary of the aspects of regulatory review that would be of particular interest for an all-electric battery propulsion system. And in that review, there was nothing that stood out as enormously complex or burdensome. They're very clear that their focus would be on a system that meets their safety and fire requirements with respect to the battery modules, that you have a verifiable or validated battery management system, you have adequate ventilation, you have fire detection and suppression capability, that the battery compartment is designated and separated, and that you have vital system automation, testing, and documentation so that you can automate the shutdown in the event of an emergency. Alternative propulsion analysis. In the report, we compared a handful of potential propulsion alternatives. Diesel direct drive, diesel electric hybrid, liquefied natural gas, and hydrogen fuel cells. The goal in this was to ensure that we were being comprehensive, that while we had some very specific outcomes that we wanted to achieve in the analysis and the data acquisition, we wanted to take a look at some others. For this route, for this run, and we speak about this in the report, diesel direct drive and diesel electric hybrid are all very viable technologies that you can utilize, depending upon what you want to do or what you want to achieve with your new ferry. Diesel direct drive, diesel electric, and diesel electric hybrid will not put you in the realm of zero emissions. You will have reduced emissions of various levels between the three technologies, but you will still have emissions nonetheless that you will have to be attentive to. And then also there will be fuel consumption, which with an all-electric alternative, you get a return on investment, as you've seen in previous presentations, with respect to minimizing or decreasing your annual fuel usage, and some trade-offs in return on the investment in the battery technology with respect to reducing your annual maintenance, spare parts, other fluids, and auxiliary system maintenance that has to go with these types of systems. You will find in the report we speak to liquefied natural gas. Our determination is that it's not feasible, or while technically feasible, it's not practical for this route. The burdens that come with liquefied natural gas lend itself to larger vessels that have a steady infrastructure established for refueling. And also it adds complexity and cost to the construction and also the engineering of the vessel. You have specific materials and requirements with respect to being cryogenic, hazardous zones, adequate ventilation. So the regulatory review and compliance goes up a significantly higher level when you start looking at LNG designs. Hydrogen fuel cells are very conceptual at this point for the marine industry. There's some demonstration projects that are currently occurring right now. As far as we could tell, there's only one vessel operating with a hydrogen fuel cell system that's based in Germany, and that's a relatively small ferry that's passenger only. So while there is potentially opportunity in the future for hydrogen fuel cells to be utilized, it's not really viable from a practical standpoint right now for the marine market space in a consistent way. And then plus all the fueling requirements that would go with it and the safety requirements and regulatory review would be of an even higher level than they are with LNG. So conclusions and recommendations. All-electric ferry, it is feasible, and it's buildable. Taking a step back, we also went and touched base with the major local shipyards. Rachel and I visited them and presented the concept, and just to get a general sense of feedback from them. We visited 3, Dakota Creek, Nichols Brothers, and Vigor Industrial. All 3 took a look at the initial concept, said it is feasible to build it within a cost and schedule that would be reasonable based off of rough order of magnitude estimates that you've previously seen. So there was no hesitancy, no major concerns in terms of their capability to build and deliver this type of new vessel for you. The technologies are viable, and what's going to determine which technology route you go with respect to all-electric propulsion is going to be a matter of determining how you want to operate the ferry. The charging scenario and the schedule are critical in that future consideration, and you have a lot of options in that regard. So Art Anderson Associates is recommending that you continue to take a close look and that you consider fully an all-electric propulsion system for a future new ferry to replace the Guimas.
Questions? Motion to extend.
So back to the chart on the tonnage and displacement.
Yeah.
Okay.
Yep.
So is the projection on the tonnage based on the vanadium batteries, or what is the determination?
It's based off of the vanadium batteries.
And my understanding, I believe, when we were touring down there, that the bank of 5 units for the batteries was probably about 80 to 82 tons.
I believe so.
Battery, I think.
Oh,
Well, it couldn't be per battery.
Pounds,
4 batteries would be
80,000 pounds.
in the report, we did get an estimate of the weight impact, and we're looking at, in total, probably 6, 7 units, containerized units, at a weight of about 250 tons. And that's what we calculated into our weight estimation.
And if we were to use the other types of batteries, it would be substantively different.
Yes, lithium ion, depending on your charging scenario, you could go to as low as 4 to 5 tons or as high as 45 tons. And that depends on the particular, I'm getting into some of the vagaries of the chemistry, but you can go NMC, the nickel manganese cobalt configuration, which has more capacity for you, a bit larger, and so that would lend you up towards the higher end in the 40-ton range. If you went with some of the newer chemistries like LTO or lithium titanate oxide batteries, those are much smaller and lighter, but not as much capacity, so you'd be charging more.
So the cost of the construction and the type of vessel that would need to be built, if you're handling 250 ton with plus the cars and everything, is going to be somewhat different than one that would have substantively less weight to be transported.
Actually, no. What we'd be looking at is in terms of the design, in terms of the steel weight, which could drive some of the labor hours potentially in a new construction of a vessel. We would design in adequate space for these larger batteries. Really the main goal in the design with respect to tonnage and the larger batteries is that you're trying to design an internal structure that allows for enough space for the containers to be placed. Because tonnage is a measure of the open space or volume, which is within the hull. Not necessarily, it doesn't translate directly towards steel weight in the design, but it could add to it. I'm not disregarding your comment. It's dependent upon the particulars. But I don't consider it a major factor in terms of significantly increasing or decreasing the cost of construction of a new vessel.
Can I just, so tonnage is a volume calculation on this chart versus what I think of as weight of the battery? Those are two, are we talking about two different measures?
Yeah, tonnage is a measure of the volume. You're measuring the internal volumetric capacity,
Okay.
and you're equating that to some sort of weight.
So I can't go and say 250 tons in batteries doesn't work in a 91 ton, a ship built to 91.
No, you can't.
Okay, I just want to make sure.
No,
because
yeah.
They're close words. And, okay.
Yeah, go ahead.
But in that, so each of these different tonnage you have on this chart here, their carrying capacity, their total weight that they can carry is much larger than bidding on design.
Yes, exactly. Yeah, it's they're told their capacity is dictated by the number of vehicles that they're going to carry or passengers. Well, passengers they want to limit to 150. Vehicles necessarily doesn't fall under subchapter T requirement. I know I'm getting into some of the vagaries of the CFRs, but tonnage is looking at the volumetric space that's contained within the hull. not necessarily its capacity or ability in terms of displacement or carrying capacity.
That's why those big container ships that are huge, I mean, they have lots of weight on them, and they don't tip over, supposedly.
Okay. Sorry to interrupt.
No, that's okay.
I gotta
So
get
the
more-
energy cost utilization of transporting, does it cost the same to transport 250 or 300 ton across the water than it does to transport 50 ton? I mean, if you were to use lithium batteries and your total weight plus the vehicle's capacity is 20% of what it would be carrying the batteries, is there no energy cost difference in transporting that?
No, there isn't. I mean, what you're looking at in the energy, what drives the energy demand for this ferry is the high current, which is dictated by the tidal shifts. And so that's why we targeted the highest power demand in terms of kilowatts and also in terms of energy consumption with kilowatt hours, because you're going to be using the most energy when you're departing the Guaymas Island terminal. And that demand will always be full open, wide throttle, full open throttle, or full demand so that you can break away in a high knot current situation. And when we did our weight estimate, we were looking at a fully loaded ferry, which is dictated by the cars, not cargo. Does that answer your question? The energy consumption, the battery size, the energy consumption will not change for the route, regardless of the battery technology that you choose. What will vary is the capacity that you would want to determine will reside on the vessel, which is based off of when it needs to be recharged.
So, Eric,
Yeah.
will the vanadium flow technology create any regulatory challenges versus the lithium battery in regard to Coast Guard regs?
It will be a new technology for them. So what I pointed out in terms of the regulatory review, when we were meeting with the officer in charge of marine inspection, he was very clear that these would be the considerations for an all-electric or battery-only propulsion system, and that these were initially established with lithium ion. So there's a track record that's been utilized, or it's being utilized, it's being put into designs right now in the United States, if not throughout the world. So you could anticipate that there would be a higher level of scrutiny, or you would spend more time and effort in ensuring in the design and approval phase with the engineering of getting VRB flow batteries, the vanadium redox, approved.
And to just kind of add to that, in the past few months, we've done a lot of research, talked to a lot of different companies and a lot of different folks that have expertise and knowledge in this specific all-electric ferry, technology. And one of the things that we've learned is that right now there's only one battery company or battery provider that actually has the Coast Guard approvals and the Class Society approvals, where actually it's DNV approvals for a battery for marine use. And that's Corvus Energy in British Columbia. So while other companies are working on getting those approvals, I'm not aware of any other companies that currently have those approvals. And then certainly, as Eric explained, getting approvals for other lithium-ion technologies is certainly going to be an easier process than starting at the beginning with Coast Guard and getting approvals for the vanadium flow battery. Also, UET does not currently have a marine battery. So, there's a number of different things that we look at, but I think most importantly, when we look at the regulatory requirements, that was a good question, Dan.
Yeah.
But the company in British Columbia is the company made the batteries, I believe, that are being used on the Ampere
Yes.
in Norway.
That's
So
correct.
it is in a ship, it is operating, and you said they are Coast Guard approved? Okay. So.
Okay.
Yeah.
Other questions, Commissioner Mason?
Your model of using the two different sorts of batteries, and one charging once a day and one charging many times a day, why wouldn't you use many times a day charging for comparison compared to?
Oh, you mean developing a scenario to present to you in the report? In discussions with Rachel, we felt that it was probably too premature to begin to work out a schedule or a scenario for the operation of the ferry from which we would begin to dictate an evaluation.
But the reason you charge more times a day with the lithium is because then you could have less batteries. And so I'm assuming with the liquid batteries, you'd have smaller, charge more.
So you can go with lithium ion you can utilize lithium ion if you want to have that full capacity to only charge once per day, but it would be very cost prohibitive. I mean, the upfront capital cost would be quite significant on the level of the vessel. And then you would have to have cell replacement strategies, and your maintenance schedule over the long term would be significant as well. So any lithium ion battery manufacturer wouldn't recommend that you purchase that level of capacity. So you can do it with lithium ion to only charge once per day. And then so in terms of what the capacity that you feel that you need based off of your charging scenario, that would dictate the size and the footprint of your lithium ion batteries. Does that answer your question?
I'm just comparing apples to apples instead of apples. Don't worry, when you're charging difference on your different analysis, that's all. And the other thing on a backup power generator or something like that, would you recommend doing that or not need that on board the vessel? Or?
I would recommend it. I think it's fine. In terms of requirements versus cost, that would have to be a determination to make with the county. The Ampere, for example, she has a backup generator. DNV did not require it, but Solus did, safety of life at sea, because they were committed to wanting to ensure that there was some means of power backup. To clarify, this vessel, your vessel, a replacement vessel, does not need to be classed by a class society. They have good design criteria that would be important to follow, and you're not required to adhere to Solus. So if you felt that you had enough reliability and safety in place or during the design development to not warrant a backup generator, then you wouldn't need one. But if you want that reliability, that backup, or that redundancy, if that's a priority for you and in consideration, then I would support that as a naval architect and recommend it.
Okay.
What is SOLAS?
Safety of life at sea. It's an extension of the United Nations International Maritime Organization. So they set rules for vessels transiting the open ocean for a number of life jackets, safety vessels, and they establish a number of requirements for those types of vessels. You don't transit in open ocean, so you don't have to worry about that requirement. The Ampere technically did because of her route, and so when Solus entered into its review, they were very clear that they wanted a backup generator. That's my understanding based off of discussions with a representative of DNVGL.
So Eric, in regard to that question, the presentation we heard last week, the lithium batteries, there's two banks of batteries that provided redundancy, and then potentially there'd be a generator on board. So the other technology, how would the backup work on that?
It could be the same. You could have
five separate.
Oh, the redundancy would be, it would still be backup redundancy. So you would have segregated battery cells that one could back up the other if one were to fail. So you'd have that redundancy. A similar construct, absolutely.
Right.
Okay.
And the other thing is you were going with the Z drive because of the currents and so forth. The current ones we have are 30-some years old, and we've rebuilt them many times. I mean, the technology changed on those, or is there?
In comparison to what you have, the technology's advanced quite substantially. You would the Z drives that you would potentially purchase or acquire for a new vessel would be very efficient, highly responsive. In terms of maintenance and warranty, you would be in a much better position than I think you are right now.
But it's basically the same thing, gears, oil, and moving back and forth, or not?
Oh, no, I'm sorry, Commissioner. What you would have is that you would have, it would be a motor mounted to the top of the Z-drive unit in the hull. So there wouldn't be in an all-electric configuration. So it would be an electrically driven motor connected to the top of the gearing on that, compartmentalized in a very specific section in the hull of the vessel. So what you have now is totally off the board. That's antiquated technology. You wouldn't have that.
Lithium-ion batteries have a history of fire. I mean, is in the marine world, do you design something to encapsulate or fireproof the area where lithium-ion batteries would be stored?
Yes. So what? In terms of history of fire, you're speaking with respect to thermal runaway, where
I don't know what it is.
No,
Batteries on the airplane catch on fire. You can't check them in your suitcase. Hoverboards blow up.
Right.
So
I bring that up, sorry, Commissioner, because it's dictated by the chemistry, and so lithium-ion chemistries they can have exothermic reactions, which causes thermal runaway, which causes the fires. So battery systems, battery management systems, and the cell technology is advancing so that you can compartmentalize the cells and contain them. But in the event of you cannot completely prevent thermal runaway from occurring with lithium-ion battery technologies because the chemistry is what it is. In comparison to vanadium redox flow batteries, you don't have that concern with thermal runaway or potential fire with respect to the chemistry. But there are other fire hazards or concerns that come with that technology that have to be addressed. So Coast Guard requirements would be very similar in terms of compartmentalizing fire suppression systems, adequate ventilation, emergency shutdown controls. Does that help answer?
I think it's a question that the common person out there would want to know if they're following anything that has to do with those lithium-ion batteries. So.
Yeah, it's a very good question, and that's what the Coast Guard regulatory requirements are set up to try to address.
Okay. Good. Other conversation? Rachel, is there anything else we should?
Yes, actually,
Sure.
Eric, thank you for presenting this today. I think you and Art Anderson Associates did a great job on the report. I just want to point out that, this process of getting this propulsion and power study took a little bit longer than we had originally anticipated. But we really tried in this study to address a lot of the comments and a lot of the concerns and questions that were brought to us by members of the Ferry Committee, members of the people who are living on Guaymas Island at a public forum that we had in the spring. We attempted to answer questions in regards to feasibility, more specifically tonnage, U.S. Coast Guard requirements, what the shipyards thought of a project like this, what the power requirements would be. And so we are hoping that when this report is released to the public, that they'll find that it was useful. Our next step is to send the report over to Puget Sound Energy, who's very excited to work with us and partner with us on a project like this so that they can review what's available from the grid, because part of what Eric was talking about in what battery technology we choose or what charging schedule we choose will be based on availability in the power grid. And that information will come from PSC. So we're excited to work with them on that. And then, Eric, I have a follow-up question for you, and this is to address perhaps some concern that will come up from the public too, or has already. There are folks that say, maybe you didn't need to do this study. I mean, there's an all-electric ferry that's operating in Norway, so in a sense, we already have a feasibility example running. And so my question to you is, could you maybe further explain to us why this study was so important?
Sure, absolutely. If I can go back. That's why this study was so important. There are very few ferries of a similar size and capacity that I'm aware of that operate in the unique conditions that the Guimas does. And working in the past with Joe Payne and with others, a straight averaging is not going to help you target an adequate capacity for the batteries that you will need, particular to these unique conditions and the service, safety, and reliability demands that this ferry route dictates. That's one of the clear things that has come through from Rachel to me and Art Anderson Associates, is that if this was an easy, straightforward route, you would just have a direct drive and some tunnel thrusters on the end and some props. But you need powerful azimuthing thrusters because the more you take a look at this ferry, she operates almost more like a tug than she does like a double-ended ferry. I mean, in terms of the way that she needs to be maneuverable and capable in that operating environment. And so for that, we needed to ensure that we identified clearly where the highest power demand was at, and that we sized a potential battery configuration that has enough capacity and power available to the operators who were clear in their discussions with us in face-to-face dialogue that their main concern is, I need immediate power available to me at this level so that I can maneuver safely.
So is the 11 days and the contingency that you've added on and the methodology you finally settled on in the whatever Cummins provided for monitoring, do you feel like you've got that's representative data? Is there a possibility of even greater outliers that we're not addressing? Or, I mean, are you confident in the database we're using for that calculation?
We're very confident in the database. Never say never. Obviously, there could be potential outliers. I mean, Rachel's indicated all kinds of unique operating scenarios that she's experienced in her time operating the ferry. And so you would always want some sort of immediate charging capability ready and available for the crew to execute in the event of. And who knows what that is, which would probably lend towards in the potential design going with a backup generator, for those events. But we feel very confident in the data package, the buffer that we put in, being practical and reasonable in our approach and our assumptions. And the report details that out. And we'd be happy to provide amplifying information to support Skagit County going forward.
Okay, great, thank you. Ken?
I think one of the more important things as well is, as a government entity, it's much more restrictive on how we can apply for funding and get funding. A lot of times we hear from the public, why are you doing all these tests? Why are you doing all these studies? Well, typically what happens is in order to get federal or state money, you are required to have these studies as well. Not only from a safety, but also just, is it going to be functional for the public? Where a private entity might be able to just say, well, Norway's ahead of us, we'll just go get their information and move forward. We have requirements here. If we're going to use state and federal money, there's a lot of strings attached, and they typically require studies, approval from the Coast Guard. So it's always, sometimes frustratingly, but it's always a little bit more complicated, and that's why we need to make sure we've done our due diligence before we take some of these steps. So appreciate the study. I think it's very helpful. I think, as you say, picture's worth 1,000 words. And hopefully there weren't people drinking coffee that caused the furthest swerving. But,
Well, I asked Rachel if she was filling in on some of those days.
yeah, kind of like maybe Director Berenson, they were letting him try to learn how to drive.
Let me off it quiet.
That's funny, he said it was you.
Yeah, well, that could be too. That's always possible.
All right.
Thank you, Commissioner. One last point.
Yes.
One of the outcomes I wanted to ensure with this is it's a package for you going forward so that when you do speak to a future potential systems integrator or equipment manufacturer, this is going to be one of the first things they ask, is they're going to want to say, okay, what's your requirements? And now you can say, here you go. This is what we need for this route. And then if they have any further questions, we can jump right in and assist.
Okay, wonderful, thank you.
Thank you.